The Pythagorean identities come from the Pythagorean theorem. If we have a right triangle, and we've discussed this when we formed our definitions of our trig functions, the side that is the hypotenuse would be called our r. The sides of the triangle that are not the hypotenuse, we would call those x and y. So that would lead us to the Pythagorean theorem, being y squared plus x squared equals the hypotenuse r squared. Now if I take this Pythagorean theorem, which would be true for this right triangle, and treat this just like I would treat an equation. For example, we know that whatever I do to one side, I have to do the same thing to the other side. Let's take everything in this Pythagorean theorem, everything in this equation, and divide by r squared. As long as I do the same thing to everything, the equation, the theorem will hold true. So when I divide, well, y squared divided by r squared, that is the same thing as sine squared of our angle theta. Y divided by r would be sine, and y squared divided by r squared would be sine squared. Plus, x divided by r would be cosine, and since they're both squared, that would be cosine squared of our angle theta, is equal to r squared divided by r squared would be 1. So our Pythagorean identities come from the Pythagorean theorem. Now we do want to have these Pythagorean identities memorized. However, if you can remember the Pythagorean theorem and divide everything through by r squared, you don't necessarily have to memorize it, but you can develop it using this technique. And this would hold true for any angle theta, as long as theta is describing the same angle. We also want to be familiar with any form of this. Treating this once again as an equation, I should be able to take sine squared and subtract it from both sides. If I do that, we will end up with cosine squared theta equals 1 minus sine squared theta. And this would be an equivalent form of that identity. So we should be able to know the basic form of the identity and then be able to rearrange it by subtracting or adding or doing anything to both sides. We should be able to come up with an equivalent form of that identity. What about tangent squared theta plus 1 is equal to secant squared theta? How do we get that Pythagorean identity? Well, let's take our Pythagorean theorem again, y squared plus x squared equals r squared. And this time, let's go through and divide everything through by x squared. Alright, so if I do that, y divided by x is tangent, and they're both squared, so that would be tangent squared theta. Plus x squared divided by itself would be 1 is equal to r divided by x is secant, and since they're both squared, that would be secant squared theta. So this would be one form of the tangent secant Pythagorean identity. And once again, I should be able to rearrange this if I subtract 1 from both sides, or if I subtract tangent squared theta from both sides. Whatever I would want to do to both sides of this equation, I would come up with a different form of that Pythagorean identity. But it's an equivalent form. Okay, lastly, let's take that same Pythagorean theorem, and this time the only thing that we haven't done, we haven't divided everything through by y squared. So let's do y squared, y squared, y squared. If I divide everything through by y squared, y divided by itself would be 1, plus x divided by y would be cotangent, that's cotangent squared, is equal to, and then r divided by y would be cosecant, and that would be cosecant squared theta. So this is where we get our Pythagorean identities, and this is why we call them the Pythagorean identities because they come from the Pythagorean theorem in our trig function definitions.